network problems and network design architectures. We're going to be talking about the data mobility exhibition today. It's a testing framework so that people can validate data transfers and cyber infrastructure, data transfer performance, and then getting into a few other things on that. And then George will take over on the specifics of data transfer nodes and things like that. So one thing about data transfer is we've coming up a lot of use cases where people do not have know what kind of data transfer they should expect. So we go, for example, when you go to, like, here's an example from, down to the NSF from where I'm at, and you can see that Google Maps gives you some expectations on time, mileage, things like that, and maybe where there's construction, other things like that as well. So you get an idea of kind of how to plan a little bit better. But with data transfer, a lot of times there's components around that are not consistent, and you're not sure what to expect or what infrastructure you have. A researcher kicks off a transfer job, and they just sometimes they get what they get. It's like a best effort piece. So what we're trying to do with part of this data mobility exhibition and with the EPOC is try to have sites that have a CC Star grant or a CC Star award project to try to get at least 1 terabyte per hour data transfer rates with what they're setting up. And we know that depends on distance and some other pieces around that, but that's a pretty reasonable benchmark to get on a 10 gig node with the Science DMZ infrastructure and components like that. So it's not going to be optimal for everyone. There's going to be people getting more than that, but at the same time, this is kind of just a benchmark to go after as you're putting these projects in. Some of the other pieces around that turns into about a 2.2 gigabit per second network rate, and then on a storage platform, it's around 277, 280 megabytes per second. So depending on the audience or your role in the cyber infrastructure or data architecture platform, you kind of have those 3 different numbers to work with, depending on what your general audience is. But to the researcher, we want to try to get at least 1 terabyte per hour with some of the things is what we're trying to recommend currently. Some of the dependencies related to that could go into some of the other pieces you'll discuss around the testing or the next week sessions, as well as the sessions later today as we get into the different components of it. But it could be related to the Science DMZ architecture, security monitoring in there. One thing, please enable jumbo frames. We have MTU mismatches and problems all over the place with these pieces. So try to make sure that jumbo frames are enabled for these data transfers. Could be anything around tuning your BGP or BGP prioritization to RNE networks over commercial or commodity networks. Perfsonart testing, which comes in a little bit later in the talks. Whether you're doing S-Flow, NetFlow, IPFix, standard system, and SNMP monitoring for your network. The individual data transfer node, which George will touch on a little bit, whether the storage is local, connected, or network. It could be systems tuning you have to do, storage tuning. And then also what it comes down to is the data transfer application or the portal or the workflow related to that. All those components really, can be one of the knobs you may have to adjust to try to get decent transfer numbers. But overall, to the researcher, if we just try to speak one level of piece of data to them, it's 1 terabyte, per time, similar to what Henry was just talking about giving time back to researchers. If we can get the data transfers up for people, then that's time they have back. So you see the tenure track he just mentioned. This could be, data transfer shouldn't be a part and shouldn't be a worry, but normally it is, or how they have to get things done and they're under pressure to get things done. So if we can get this right, then that's one less thing they have to think about and worry about. So we have a data mobility exhibition program started around this. This goes into the different pieces around the cyber infrastructure that people work with, whether it's computing, data, or the science networks. All those pieces are relevant, but a lot of times they're out of the researcher's control. So through science engagement, we can actually go out and try to understand the workflow and try to find any one of those pieces to try to tune to try to get the data transfer up, as well as the research workflows. So this is just a common problem that is out there, but a lot of the times it really depends on numerous things or a subset of things to work on, where other things may be working well. It may be 1 or 2 things, or it may be an entire ecosystem that needs to be adjusted. But overall, a lot of times through science engagement and working with people, we can understand and we can try to take some of the IT problems away from the researchers and try to get things just operating more efficiently. So this kind of helps streamline the process and letting us back to writing grants and doing research. So the data mobility exhibition started out with just some initial testing. We recommended this at the 2019 CC Star meeting. It was kicked off then. There's a way that you can participate in this. You can use reference data sets to test your existing components, your cyber infrastructure as you're going through this, and as well as you're making changes, any sort of updates, you're putting in a Science DMZ, or you're putting in a Science DMZ concept for a different type of data set or a different type of workflow or instrument. All these things can be reference tested with this program. So going forward, you can download or upload data sets, measure accordingly, and then, like I said, if there's opportunities to improve, you want to see how far you can get, we can help you with those to try to get those pieces tuned out. So the steps really include on this, and some of these are relevant to what you need to report on your CC Star anyway, so you're kind of already doing the work. It's just, see what we can get here. So do a 1 to 2 page description of your network and data architecture, which is, CC Star reporting piece. Do a data transfer, get a data transfer machine set up or use an existing machine. In this case, currently we're using Globus to do the transfers, so we have to get Globus on there to do the transfers to and from. Download or upload the reference data sets accordingly to get the results from what we need to do to baseline the tests. And then from there, share your description, your results, any outcome you may have, any improvements, any discoveries. And then again, if you need any support on this, the EPOC contact information is right here. But a few of these components, other than uploading and downloading the data sets, are CC Star reporting components. So you have results from where you started through the changes you've made to your final result. A lot of these things, this platform and framework will provide you data according to these pieces. So the current testing framework endpoints, there's one, they're kind of scattered throughout the US, which is actually great. There's one in New York at Ithaca at Cornell. There's another one in Boulder, Colorado, and there's another one in Argonne. So they're kind of in different parts of the country. You can test to and from. In addition to, there's also Google Drive and Box. There's an endpoint that are out there in the cloud if you want to do data transfers to these cloud sites to verify. And in addition, the ESnet has a 40 gig node that we're working to get the DME data sets on as well. So that will be coming up in the future. So related to this, as part of your CC Star, a lot of times you need to do a timeline and a project plan related to this. Here are how some of the components, this is an example of where in your timeline of your CC Star project implementation, this could also be related to the DME, has very similar components to this. So as you start off in the second column in, you see the baseline current state of your configuration. So you kind of go through those steps anyway. This will allow you to get a baseline and document, where things are, the components to it, before you do any sort of changes at all related to this. And if you do the transfer of the data sets, you can actually see, how well things are performing, what kind of numbers you're getting, and you can document those results and then have this accordingly. So it's kind of like your steady state or, level 0. As you get your Science DMZ installed or your project's kicking off, as you get, maybe a component change and an upgrade done, or the prototype built, you can actually go through and retest those reference data sets and then go through the results. And again, if you need any assistance on tuning these pieces, EPOC would be available to, run some tests and also provide guidance and assistance on that. And typically, then that could be part of your year 1 report for your CC Star with some of these. Then you actually have, where you were and where you're at now type information for your first year report. Going into that a little further, as you do other tuning components or as the project matures and say, phase 1, 2, or 3, those again can be repeated through that middle column as you're going through that. And as you can see, you're kind of doing the same work over and over as you would do this and to try to gather reporting data. That if you install a DTN or some kind of GPU processing thing or whatever you're doing as part of your project, again, once the change has been made, you can rerun data sets to and from this, depending on where your system or your project is going on. And then as the final report, if you run the data sets and you reproduce and update your network documentation, your data architecture pieces, you have results from this, then you have your final NSF report. You have data components to this anyway from this. So this DME framework allows you to gather some data out there from known tuned endpoints that can be relevant to any sort of data transfer related to your grant. So if you'd like to automate some of this, there is a link right there. You can actually do some scripting. You can do some automation on this to cut down some of the manual Globus transfers in time. The link to the DME program is right there. And then if you're going to need any further assistance, the EPOC information is there. So any direct questions? Otherwise, I hand it over to George.
What's a good, is the EPOC email address the best place to reach out to you guys when we're ready to get to that step?
Yeah.
Okay.
Yeah, it opens a triage. There's different tickets you can go through.
Great, thank you.
Yep. But like I said, we're trying to standardize this here and just try to recommend people try to get to 1 terabyte per hour, at least for the researcher's sake. That's pretty reasonable on the network. It's not very intrusive on a firewall or things like that, or on a Science DMZ or a storage subsystem. It's not, it's not too high, but like I said, we have a lot of sites that are not at those site levels yet. So that's what we're trying to recommend is 1 terabyte an hour. So. All right, I'll just hand it over to George.
Hey team, I'm going to attempt to share screen and we'll go from there. In theory, I'm sharing.
Yeah.
Excellent. Okay, it's really hard to follow up Alex, Henry, and Ken. Don't know how I'm going to do this. That said, I'm George Raub. I'm wearing 2 hats today. The Engagements Performance and Operations Center. I'm a performance chaser. I love trying to tune things and make things faster. And then ESnet, infrastructure platforms and service support. So I'm a sysadmin by trade is the best way to describe it. This talk is about DTNs, data transfer nodes. So I'll start out with defining it. Simply put, a data transfer node is what a DTN is. Keep in mind, it serves science first. They are designed and tuned for data movement. They are supposed to solve a specific problem first and then have fun later. That said, they're extremely fun to tune. Wait until you see the Perfsonart talks and some of the fun that can be had with tuning DTNs. All that said, don't get lost in the speed and the feeds. And I go back to the very first bullet point, and this gets lost quite often. I even fell into this trap. DTNs serve the science first. Why do we have DTNs? Well, as Alex was mentioning with the amount of data that's flying around, as all of you are aware, there's a lot of data that needs to get from point A to point B. So usually they're purpose-built for closed set problem definitions. You don't want to compete with other resources. You want to have an excellent security posture, and time on the wire is time not doing science. So again, back to the whole idea of the part that Ken's talking about, right? Let's get 1 terabyte an hour. Let's see if we can hit that. And then let's get it accelerated. We want to easily translate and ship data from an instrument or cluster attached storage, and we'd like to be able to schedule these. So DTNs are excellent. What are the elements that make out a DTN? It's mostly a balancing game. We're trying to find the balance between 3 major adjustments. Think about the triangle. You can have cheap, fast, or good. This similar situation, we have 3 major adjustments: CPU, storage, and the network interconnect. So let's start with CPU, central processing unit. It's a balancing act of cores, clocks, and threads. Back to your problem statement of what are you trying to solve? How are you serving the science? So do you need just a quick and easy 10 gig DTN? Do you need to move 1 terabyte an hour? Do you need to just get a couple of small data sets here? Are you moving exabytes? Do you need a fleet of DTNs? Threads and flows, that goes back to core count. Memory storage and stewardship, right? So I always talk about memory, and I have kind of a nervous tick about take a look at your processor type and make sure that your memory channels are fully populated. And then another component with your CPU that as you make the selection, is it cluster attached? Are you going to have to give a couple threads and cores off to ensuring that you're able to keep up with your Lustre file system or your GPNFS, or encrypt and decrypt if you're in a secure environment? So when selecting a CPU, keep your balance in mind. Are you serving science, Are you meeting the problem set? The storage. Again, this is a balance, and I left an extra bullet point that's empty. Apologies. Speed, capacity, and cost, right? What we got in this situation is we've got to think about how we're getting that storage onto the wire, right? So in certain situations, RAM is part of the storage. I'll mention are your channels fully populated just because, but that said, it gets into the speed, right? Are we trying to get it off flash? Are we getting off spinning rust? Is it meeting that terabyte an hour baseline? And there's times where the spinning rust actually is useful. It has a place. It's very meritable. We'll talk about that a little bit when we get into the RAID components. So the RAID components themselves, we're looking into what are we trying to accomplish? Do you need just something that works? Kind of like Henry was mentioning, do you need the 5 nines or 5 nines, right? Or 9 5s, right? So if you think about what a RAID card does, it can abstract away hardware failures. It can make it so you get a blinky light, you pop it in, go, it's up, it works, it's redundant. This is great for instrument situations. You know you have a small closed data set. This RAID set needs to be protected. It's a golden copy. Let's get it from point A to point B. Hardware RAIDs are great for being redundant, plug and play, and hands off. That said, there are edge cases. When you start getting beyond what the cache of the RAID card can do, you might clip. You might hit limitations in the RAID controller when you go for firmware updates, performance changes, growing them. If you build a RAID set out as a RAID 6 and try going to RAID 10 later, that might not be a case where you have to completely format and restart from scratch. Other cases are where in the file systems, you can completely eliminate a RAID setup. And I don't want to say eliminate, but think of it in a different way. I'll call that a file system called ZFS. Some of you may be using it. If you haven't used it, take a look at ZFS. It's taking out the RAID controller using HBA and JBOD, and then augmenting it by bringing in RAM as part of the file system and tiering it. You can have it completely layered. It's insanely redundant. I put asterisks by plug and play in that you do have to have some systems administration knowledge to be able to install it and keep it maintained up and healthy. Performance and capacity, sky's the limits. Growability, amazing. And again, RAM is truly storage in this case. So one of the limiting factors on like a RAID file system or a RAID controller is you have a certain fixed amount of cache. In a ZFS type of file system, you can just expand out your RAM, and at that point, go. You need more capacity, add more spinning rust. Appliances. I want to make a call out to these. They do have a place. There's times where that's all you have. And there's even some large scale facilities that have had to revert back to using appliances. And when I think of appliances, I think of consumer grade network attached storage devices, Synologies, Drobos, so on and so forth. They're redundant, they're plug and play, their performance and capacity are questionable, and you can paint yourself into a corner real quick. I'm not saying that they're bad, I'm not saying that they're good. If it's getting the science done, go. By all means, use it. That said, when you can construct a DTN and when you can use a DTN, by all means do. If it comes down to having to use an appliance to get the science moving and out the door, that is a valid answer. Use what you have at your means to be able to help science. Again, we build DTNs to serve the purpose of science. DTN placement. Talk about the rock and the hard place, right? So all of us are on research networks. All of us are on campus networks. All of us are on enterprise networks, right? Where do we want this? Where is the security posture? How does this all fit? Sometimes they say, like I put in the quote, you know, go fast, you go alone, go far, go together, right? So if you're trying to bring the science along, you've got to have it placed in a very elegant way, right? We all know about the Science DMZ pattern, right? We all know about working with your networking team. We all know about ensuring that placement and security are a good position. So placement, it also ties into to go fast, right? So go fast or go together. To go fast, do we really need 100 gig DTNs? And this is where I get wound up in the speeds and feeds, right? If you're going to be and place your DTN well and be a good citizen and a good community member, and you have 100 gig DTN, but there's other people on your regional, and your regional might only have 40 gig uplinks, I don't think your 40 gig or your 100 gig DTN will perform well or be very friendly to any of the other people along that line. So keep in mind on your sizing. That said, 100 gig DTNs would be awesome for land scale, right? If you've got 100 gig from point A to point B, building A to building B on your campus, go. Is it an instrument into your cluster? Go. Basically, are you in this together? Are you building a DTN to help the science and to help the teams and be part of the community? To go far, we're thinking about science in the DMZ. We're thinking WAN scale. We're thinking what's out there, who are we going to impact? This is instrument scale and clusters to peers or cluster to cluster, national research to national big data hub, your cluster to Henry's cold storage, one storage, right? We're trying to get it to archive. Where are you moving this to, how and when and why? So basically, not are you in this, are we in this together? Is the whole unit, kind of talking again about Alex's global supercompute, this kind of nods to that. Again, the how we can see what's out there ties back into the DME, and wait until you hear about the Perfsonart talks. What's out there? How can you be the best community member? So to answer the question, where do we put our DTN? It goes back to the problem statements of what are you trying to solve? How are you helping the science? So get your sense of scale. Again, back to the DME talks. A terabyte in an hour, a terabyte in a day. Do you need a terabyte in seconds? What are you trying to solve? So that will help your placement. Don't work solo. Work with your community. Work with your local network engineering. Work with your regional. Go larger. I noticed in the chat there was a discussion about BGP. Work with your community. Engage with EPOC. We'll help and try and get as much as we can to talk. Putting on my ESnet hat, we can try and decide or assist with your regionals and see where the pathing goes. And there's possibilities. There's elegant cases, right? Data to fiber. You're on campus, instrument to cluster. That's probably the easiest. There's also complex cases where you have cluster-based file systems with scheduled I/O, or long haul, where science knows no bounds, right? We're trying to get from an IoT device in an Akamada desert all the way across to a regional storage. How do we do this? So think about your use cases and think about serving the science. Let's talk about the elegant case, data to fiber. It's not always elegant. There's cadence of transfers. Is it going once a second, once a minute, once a day, once a year? How often does that data come in? Is there time for data validation? Are you doing garbage in, garbage out? And then simple flows can take strange paths. You might have it going out of an RNE across a commodity and then back down to an RNE. Know your pathing. Again, I'll talk about reference the Perfsonart and the DME. Know your pathings. Don't hesitate to reach out to your regional or your network teams. Know your paths. Test your paths. Prove it. The elegant cases can also have capacity woes, right? You could be bumping your head against network. You could have network cables. Transducers go bad all the time. You can have storage failures, too small CPUs, capacity woes, right? And then again, back to call out the let's go far. Let's do it together. Be excellent to each other. If you have a closed set, you know where you're going, you know what the team's doing. Moving together can really help. Communicate what you're doing. Share with the community cool things that you do or failures. When it blows up, it's sometimes fun to watch the parts go across the track so we know how not to do it. Elegant cases also our instrument or cluster here to WAN and beyond. Sometimes it's just clusters that are trying to schedule out to an instrument or just another file system. Sometimes just, oh wow, like we're trying to get a parallel file system that's the output of XYZ going all the way across the WAN to another institution into a pipeline. Introduce cloud, and you don't even know your endpoints at times. So again, know your peers. Don't hesitate to call for assistance. Diving into all of that, tuning a DTN. I'm showing a Quadrajet Rochester carburetor that I did a rebuild kit in to change out the Bakelite float to a brass float. A lot of moving parts. There's a lot of pieces. Communicate. Tuning it is finding the balance, and it's come back to your problem statements, right? If you focus your design around what you're trying to solve, you may find that a simple 10 gig RAID elegant 1U node will do everything and beyond. Other times you'll find, hey, I need a multi-core, all the RAM, and guess what? We're connecting up to Lustre at the same time. It has to meet your needs. Make sure it meets your mission statement. The problem statements help focus the design. When you have the focus, you can get the balance, and you can get the placement. Keep track of the changes. This is one of the parts that I always have fun with. You change one variable, you know what happened. You change two, you're not quite sure. Change 4 or more at once, hey, don't know. So patterns help solve the issue. Don't hesitate to keep your parts in track, keep a list, and also it helps for reproducibility. Tune one element at a time, I called out. So something as simple as network tuning, right? This is a pattern that I try following, right? I'll start with the firmware and the drivers. Out of the gates, am I up to date? Is my firmware latest? Are my drivers happy? Next, dialing up the resolution. Let's look at congestion control. There's been some excellent talks on BBR and congestion control. Out of the box, don't necessarily agree with it, but you can always improve performance a little bit. Measure, improve. Ring buffers are my next level. Then I go into CPU pinning, and then I get into pathing. And you'll notice that I'm also taking this from a sysadmin perspective, right? I'm trying to tune upward. From a network perspective, it's always the MTU. If it's not MTU, it's DNS. If it's not DNS, it's path, right? So work together. This can't be done in solo. You can be tuning something against something that should not be tuned. CPU, the heart of the beast, right? Take a look at your BIOS settings. I can't count the number of times that BIOS settings have actually bit in a bad way, trying to do the right thing. Example being, look at interleave on your RAM settings. Are your RAM channels fully populated? Other things, power savings, right? Power savings is good, but it takes spool up time. So you try running a tuning test that's not fast enough to spool your clocks up, you might get faulty tests. Vendors often have excellent guides. Don't hesitate to work with your SEs or your vendors to find a performance tune, not kidding around. I'm doing this as an HPC workflow, and they'll probably have a white paper on it. Power or thermal concerns. I've been in data centers before that had suboptimal cooling. I have seen DTNs and HPC nodes clip thermally. You'll get cores that'll thermally clock down. Again, monitoring and baselines, that's such a vast topic. One of these days, I'll probably generate a slide deck and we can go over monitoring baselines. But it goes back to know what your baseline is, tune against it. And then again, interactions with storage and are your RAM channels optimized? The interactions with storage are a huge factor. Are you able to get the data from your storage to the wire, and is the path clean? Let's see here. I've got just a few left. I'm trying to do a time check, sorry. Storage. Okay, same situation, latest revisions. RAID firmware, is it latest? If it's dedicated, make sure that RAID firmware is up to date. Make sure your drive firmwares are up to date. If it's an HBA, similar situation, make sure your drive firmwares are happy and healthy. On the file system, ZFS, are you running the 2. series? Are you still back on a .7 release? Is it an OS appliance? Hey, again, are we the latest OS? Back to the firmware. Are there tunings that can be done? There are things that can be done to appliances that are pretty impressive to make them move. Maintenance concerned. Have you calculated that in? There are times when DTNs need to be taken out. Do you have a backup DTN? Do you need a backup DTN? Kind of back to what Henry was even saying, can you live for 8 hours a month of downtime? don't hesitate to factor that in. Make sure that your DTN has a data plan. And failures do happen. And again, the community, right? So all together, share your failures and successes. Don't hesitate to say, look, I tried, B-tree-FS on top of Lustre, on top of ZFS, and guess what? It blew up. Well, that's useful to others. Let's not try trying that. Community participation, share what you do. Maintenance concerns, don't hesitate to be vocal on your pain points. If you know network maintenance is going to inhibit elephant flow, don't hesitate to work around to get your own maintenance window or data transfer window. Make sure you're placed in a Science DMZ. Or if there's something where the security folks say, no, this can't go in a Science DMZ, have them justify why. Likewise, have them work forward into your Science DMZ patterns. Great talks on Science DMZ that can be referenced. Again, get to know your network folks. I can't count the number of conversations that I've had with regionals. It's just been awesome. There's so many fun things that you can have just by talking with network folks. Buy them a cup of coffee. If you're a network folk, thank you. Ask for help. Epic, reach out to the Epic team. We're happy to help. We want to hear successes and failures. We want science to happen. Everybody needs this to happen. And then data movement plans. I can't say enough good about data movement. What is your network data plans? What are your research data plans? Overall, collaborate and enjoy. Let's get the science moving. Let's get these D10s humming. Thank you. Thanks for letting me have a talk, and I'm all ears for questions.
So you say that all elements are key, and I can appreciate that. I was wondering if there's like a top 3 that covers like 90% of the cases.
Yeah, that's a great question. So a top 3. Number 1, what's your purpose in the science you're attempting to do? So you need to know your scale of data movement. You need to know the cadence of data movement, and you need to go know your points A to point B. So I'll fall back to observe, orient, decide, act. Observe your surroundings, orient your direction, decide on your plan, and act, in other words, implement. So from a DTN construction from the hardware perspective, clock speed, your file system decision. So are you wanting to use RAID? Are you wanting to use a more exotic file system? And are you cluster attached? And then network, right? So that one gets more complex. And that's where I'll say, let's not go 100 gig DTN just because you can. You can go 100 gig network cards and then optically clock it down. Go as large as necessary, but be tuned as much as possible. If that answers the question. So the top 3 would be know your purpose, and then dive into the hardware after the purpose, and then be friendly to the network.
I would say on the data mobility and data movement side, I agree with George. I think the network path, BGP set up to go RNE preferred through your regional and through over the national backbone is a definite, network path is a big deal. Make sure you're checking your MTUs all along the way in the path that bites so many people. So there's 2 components I would definitely add as well. So
that's great. Thanks to you both. Are there some places where we can get something that's easier to more of a cookbook style of thing where somebody spec'd out hardware and then all these tweaks that you need to do for that particular hardware for some of these high volume nodes?
We have some reference architecture out on fasterdata.net. Let me actually copy and paste that into the chat. There's also the Epic team is working on a snippet for a off-the-shelf 10 gig with RAID, just to get your toes dipped in. So there are some more resources coming. As the community has questions or wants to build a standard around it, keep the questions coming. As prescribing a canned solution, that becomes complex because it defeats the purpose of what the science is that's happening. Example being, I don't believe a simple 10 gig RAID solution would work very well for Alex's workflows. He's doing very large data sets, and I think a 10 gig with a RAID would clip. And when I say clip, might get stalls and data transfers, might see performance degradation, or might not meet the need capacity-wise.
Okay, well, I understand that, but by the same token, a lot of folks find it hard to define all of those parameters from the get-go, and they just need something there so that researchers can get their feet wet and see what's going on. So I think in that case, the 10 gig could make a lot of sense for folks, or possibly an even higher speed one.
Excellent. In that case, what I would highly suggest is making sure that it is a purpose-built node. Whether it be a node that's just purpose-built, it's dedicated, it has DTN in its name, start with that. Make sure that it's designed to be resilient and that it's on the preferred DMZ. That's the first step.
Okay, great. Thank you. All right, any other questions from the group? All right, well, I will extend my appreciation to both George and Ken one more time. Thank you very much. Jason, are you ready to roll on designing, building, and maintaining a data architecture?
I think so. We're going to see if I can actually share the screen here. So first of all, can you see that?
Yes. It looks like you're sharing your desktop.
Okay, and then let's see if we can't. Oh boy, there we go. All right, now let's see if I can get into presentation mode. All right,
Yep.
Hopefully that. Okay,
that looks great. Thank you.
We're good to go. This is the third time I'm running Teams today, and it's crashed both times. So hopefully,
oh no,
hopefully we will make it through this. For those of you who don't know me, I'm Jason Zarowski from ESnet LBL, and I'm also the co-PI on the EPIC project. I work closely with George and Ken and Doug, who will go after me. And we typically do this talk first, but I had a bit of a conflict today. So there'll be a couple of things here that allude to the parts that you've already heard that George and Ken were talking about with regards to data movement. So I'll go faster over those. But what I'm going to try to focus on here is the more high level. So you were told to build a DMZ, and how do you go about doing that? And I'm going to start using a different term here. It's a term that I've been trying to encourage people to think about more than just a network architecture. It really is a data architecture. And I'll get into why that is as we sort of get through this. So a couple of pieces of this talk, I'll give a little bit of a motivation, and then we'll go into some details about how you can construct your solution space, and then how to put it all together, and then hopefully leave a little bit of time for questions for people who have them. So first and foremost, I like to start with sort of the expectations. You know, what are you trying to do here? You know, how do you prepare for research use of technology on your campus? You know, if your answer is, well, I'm here just to build the network, you know, that's not correct. We want to be able to improve scientific outcomes, and we certainly need to do so in a measurable way. So there's many things that you need to consider as you go about doing that. And I don't want to overwhelm anybody, but, you know, we have to make sure that we can see what we're putting into this and make sure that we can measure the outcomes and tie them back to real scientific results. You know, has it and will it all work as expected? You know, this isn't just plugging in wires. This is making sure that the users are happy as well. And we want those people to be satisfied. You know, the researchers are the survey population here, not just your IT colleagues. And most important, how do you know when you're done? And are you ever done? Is this the sort of project like painting the Golden Gate Bridge where you get to the other side and then you have to start on the other side again because it's always just going to be a work in progress? So this content is not meant to necessarily be a build from the bottom. It's a bit of a reset. You know, we don't want to build IT for the sake of building IT. We want to be able to tie these things back to the use cases. And to that end, this was a slide that our old ESnet director, Greg Bell, was very fond of sharing, and I still continue it to this day because I think it makes a lot of sense, is that the network isn't just infrastructure anymore. It really is an instrument because it links all the different components of the CI infrastructure. It links together the sources of the data with the places that are going to store it and visualize it and process it, and all the people and things that happen to be in the middle. Connectivity is really just a first step in this entire ecosystem. Usability is really what we're trying to do. So where do you go from there? Who and the why are two of the most important questions, I think, that are often glanced over as we get into this. We're not just building the DMZ so that we can say we have one. We have to know what those users are. We have to understand their use cases. And then those things are going to guide the technical solution. The technology is simple when it comes down to it. We can all pick things out of a catalog. You know, we're at the point where we can do that. And most technology is going to do what you ask it to do. But we need to figure out how to glue that together with what users are attempting to do on the network. Sometimes the users don't need a big network. Sometimes they need other aspects of CI. And part of understanding what they're going to do and how they're going to use it starts with that conversation. So here's our solution space, and I'll go over these semi-quickly. In fact, I probably won't spend a whole lot of time on data mobility since we just covered that. But understanding what that solution space looks like, getting into a little bit about how network protocols work, some of the architectural and design pieces, a little bit on monitoring, which Doug will go into a lot more detail after me, and then a little bit on security and policy and usage. So the common theme and new mindset that I want everybody to walk away with here is that we want a data architecture. And to get there, you need to understand the entire workflow of any given user, right? And cradle to retirement home, I don't like to say grave. But for the most part, this implies all the different things that the person is going to do when they are trying to interact with the technology stack. It's creation, it's usage, it's transfer and sharing, it's curation, and then all the other steps that are sort of associated with those. But those are the major portions of it. And whatever you do, whatever you build, it must be usable. If it's not usable, it becomes this walled garden. And if it's a walled garden, what's the point? Nobody can get in there and enjoy it. We need to make sure that people can be easily onboarded and integrated into this thing so that they can use it to do their work. It must and certainly has to be defensible. If it's not, you know, it becomes the Wild West. And we want to be able to control the users, the use cases, and we don't want this to become this big open space where anything goes. And we don't want that mentality to trickle down to the user level as well. The DMZ should be this shining beacon that you are selling to your incoming research faculty and your existing research faculty as a way to get their data-intensive science workflow done. And because of that, it must be defensible and something that you can upgrade over time and use. It needs to be scalable as the demand grows, because you're going to start with understanding a couple of key use cases, but eventually others may spill over to it. So there needs to be able to be ways to upgrade it. And it isn't just upgrading speeds and feeds. It's upgrading use cases, security policies, and things to adapt to whatever happens to be coming down. And it is an institutional capability and source of pride. You know, you're going to spend a lot of money on this, whether it be the NSF money or your own, and it needs to be created and marketed and operated correctly. So a couple of preliminaries about how this thing is going to operate a little bit closer to the bare metal, right? So it all starts with TCP. And data mobility, for the most part, has to understand a couple of key things, right? In the enterprise world, things just work. You plug them in and they work with default configurations, and networking sort of just happens, right? For science use cases, it's a little bit different. Some of the things that slow us down in the science use cases are the fact that it's just so easy for things to work if you pull them off the shelf and turn them on. As George noted, tuning is an important part of this entire step. So things like default host configurations, whether it be the TCP stack or file systems or NICs, all of those things don't necessarily work right away for the scientific use cases. In a quote-unquote converged network architecture, it's designed for sort of the common use case, which is commodity traffic. It's your web and email haystack as the users arrive for the day, or now that we're all working from home, as they turn on for the day. Things start to escalate through the middle of the day, then they die off at the end. Science traffic really doesn't follow those patterns. It follows completely different patterns that are sometimes unpredictable, and it's bursty. And because it's bursty, that doesn't always mix with the commodity method of working. Conventional security tools and policies will not scale. Conventional security means I don't trust anything, and I need to be able to put things in place to protect against the unknown. And that's fine. We accept that, and we have to live within those boundaries. I would contend, and years of evidence prove this to be correct, is that you can understand what a science use case is if you watch it close enough. It looks like bulk data movement. It looks like streaming data. It looks like it's going to well-known locations that don't really deviate too much from what they may be when they are first set up. We can set up security policy that protects and is able to have that sort of activity flourish, and we don't need to use a firewall to do so. We can use other tools and methods that still allow it to be performant, yet just as secure, if not more secure, since we're watching it a lot more closely. Legacy data transfer tools like SCP and rsync and some of those things, they work, but they're not going to scale. And scalability is a big thing as we start to talk about some of the big scientific needs. So we need to upgrade our expectation with tools. And then lastly, we can't wait for the trouble tickets to come in. We need to have constant and ongoing monitoring so that we understand what's going on with the local, the metro, and the wide area networking. Why do we do all this? We do this because of the protocols that work under the hood. So TCP, like it or not, is one of the most prevalent and used protocols on the internet. It's used for almost everything that is on your regular PC, and unfortunately, it's used for a lot of the high performance stuff as well. What does this mean? Well, networks provide connectivity between hosts, as we've seen. And how do hosts see the network? Well, from their perspective, the other end is really just a socket, right? It's a call that you're able to make into the kernel, and you can shove some information into it, and then it magically reappears on the other side because the protocols make that all happen. And it's easy to make applications use this, and it's reliable, and we don't have to worry about much, which is, of course, why they use this. But it's a fragile workhorse, and for good reason, it's timid. Packet loss is interpreted as congestion, and congestion happens. We have busy networks, and sometimes we're going to see this behavior. And TCP is designed to back off its performance whenever it sees something that may be going on in the network, because it doesn't want to overuse and flood everything, because we had that problem back in the early days. And because of that, we often have to design our applications and our use cases around the fact that we know that TCP is going to back its performance off, and we need to have these clean and fast networks under the hood as a result of that. So a lot of what we say is we're designing our approaches here because of the way that TCP works. I'm not going to go into things like BBR and some of the more advanced protocols in this talk. They do exist. They are a little bit more friendly and loss tolerant, and there'll be a couple of exercises that Jorge and his team will go over on the 15th with everybody. But for the most part, just imagine that we're talking about TCP here. So I can't do the live demo today, but for those of you that have seen me give the live demo before, this is the classic graph of, a little amount of packet loss really makes TCP unhappy. And what you're looking at here is a couple of plots of performance over time. The way that you interpret this graph is that the left-hand side is your throughput. That's listed in megabits per second. The bottom is listed in round-trip time in milliseconds. And then we have 4 distinct plots. The purple plot, the one on the top there, is our ideal use case. This is what you would see if there was no packet loss, and I was measuring performance between 2 hosts that happen to be those milliseconds of time away from each other. So if we're in the same data center, let's say less than 5 milliseconds, and I try to talk to somebody down the row, I would expect to get near 10 gig performance because the protocol is close enough. There's no packet loss. I should be able to do quote unquote line rate between them. You're going to see a natural degradation as you go on. Latency does make performance go down just a tiny bit. And it's only because the algorithm needs that much time to be able to recover as it gets further and further out. You know, it's still able to grow. It's still able to do pretty well. And in fact, it may even do a little bit better because this graph was captured a couple of years ago and hosts are faster and memory is a little bit more plentiful. But, you know, for the most part, you're going to be getting in the 9 to upper 8s of two well-tuned hosts talking to each other as they get further and further away. In the packet loss situation, and note that is not a typo, it's 0.0046% packet loss, which is about equivalent to one out of every 22,000 that may be passing through an interface. With that even little minuscule amount of packet loss, you're not going to feel the pain if you're really close in. So if we're still in that data center, less than 5 milliseconds away, that little tiny bit of packet loss may result in a couple of blips, but we're still seeing 7, 6, 5 gigabits per second. You're not going to bat an eye at that. As you get further out, and the magic number is usually a little bit beyond the 10 millisecond range, that's when things start to really degrade. And constant packet loss, even at that small little tiny blip point there, is going to make things perform less than a gigabit per second, in some cases less than a couple of megs per second. And from a user's perspective, they don't understand all what's going on under the hood. They only understand one thing, and that's sort of their expectation, right? So if they're seeing that their throughput has dropped into the megabit levels, and they know that they're connected to 10 or 40 or 100 gigabit per second network, that's going to be frustrating to them. And we don't also know where this packet loss is occurring. Note that, you know, this is what we see, but we have no understanding of where those are being dropped. Is it a busy local switch in the data center? Is it something failing off on a regional network that we don't control? Is it something that's on one of the transatlantic links? We don't know. So this is really the myth and the frustration that we often have to deal with if we put ourselves in the user's shoes of just trying to move information on an end-to-end basis. I'm going to pause for a drink there. If anybody does have questions, like Henry, I like to be interrupted, so I'll pause for a second. Okay. So the Science DMZ model is designed first and foremost to be performance-based. What we're doing with this is that we want to instill a couple of key items here. It is dedicated infrastructure, and its job is to facilitate wide area data transfer. It has well-configured hosts, highly capable devices. It's a high-performance data path, which does not traverse a lot of the commodity stuff that may exist in the LAN today. So think of it sort of as a bump on the side. Trying to go in and construct your DMZ in a legacy network and have it extend out to every single user's desktop usually doesn't go very well. I know some places try to approach it this way, but we usually advocate for, if you're going to design this thing, build it off to the side first. Just like if you're trying to build a bridge that has a lot of traffic on it, you don't necessarily want to be tearing it down in the middle of operation and then building it brand new from scratch. You know, it can be built off to the side and then you allow traffic to come onto it. We also want to make sure that we're installing a couple of other policy level things. We want to have operational models that are proactive, that enable performance, which basically means we need to have measurement going. We want to have periodic testing so that we can understand and locate issues quickly. And our security posture must be well matched to the high performance science applications. I'll go into detail on what that means in a little bit. So this is the classic DMZ in one slide. 4 components. Everything there must be considered and a part of this solution space. We do need to have it be friction-free, which basically means highly capable devices that can do wire speed, deep queues, that they support the buffers that we need for the data transfer activity. You could support virtual circuits if you really need to. A lot of people do go this route because a lot of science activities are using this anymore. We want the security policy and enforcement to be specific to the workflows. What that means is that you understand what the tool's doing, you understand what the user's doing, usually by asking and observing, and then you tailor that security policy to what they're trying to do. Just don't plunk down a firewall in the path without understanding if they need that or not. You can get the same amount of security, if not more so, just by talking to them and understanding what's going on. Located at or near the site perimeter, and I have a couple of diagrams that'll show this. For the active data transfer, do them through the DTNs. As George noted, this is a dedicated machine. It's designed to do one thing and one thing only, which is move data, and it's designed to do it well. It's going to have special hardware, special OS, all the libraries are optimized. It's not going to be running a general purpose login. It's not going to have Flash or web browsers or email or calendars or any of that stuff on there because it's there for data movement. We can lock it down as tight as you want it to be. It doesn't need to have SSH open. It doesn't need to have any other applications running. It can basically just have the data movement application, and that's it. You can implement that sort of security in the silicon on the device itself or on the first hop router or whatever the case may be. Lock it down as tight as you need to, but make sure that it can do the active data movement efficiently and that people know how to use it. And then lastly, we need to have the performance measurement and testing and the engagement with end users. This isn't the end of your conversation with them. You're going to be talking to them a lot to make sure that they understand how it works. So that's all the stuff in one slide. There's also the one picture, and this is sort of the classic pitfall here. We can go about trying to do this in terms of a design, but we want our user experience to match what that design is going to be, and that's why we need to have that last step of the engagement. So I'll pause right there before I get into the next section if anybody has any questions right now.
Yes, I got a couple of one question here. You talked about TCP. Will you encourage or advise for company to use appliances that do optimize TCP dynamically? I'm talking about appliances like Riverbed, load balancer that you can actually optimize TCP, even Cisco wars and things like that.
Not for your DMZ. I think if you want to use things that are going to optimize TCP, those are more for the enterprise network. The whole purpose of the Science DMZ architecture and paradigm is that you're trying to optimize TCP. You don't need an appliance to do that for you.
Thank you.
Any other questions? Okay. All right, so let's show a couple of pictures here. Science DMZ can take on many different forms. It all depends on what you're trying to do here. I'm going to show a couple of these. There's a lot more on the website. For brevity, I won't go into all the details here. But the key point of concentration that we want to do is make sure that we are eliminating sources of packet loss. All right, so here's sort of the first approach, which is the legacy method of what usually happens if you don't plan ahead, right? So this is somebody goes out and they get a data transfer node. Maybe they go to a workshop like this and they hear about George and his magical data transfer node, and they want to install one. So they go out, they buy it, they stick it under their desk, and they turn it on, and they hope for the best, right? So what does that look like in practice? Well, it could look something like this. We have the wide area network on one side, we have our high performance data transfer on the other side, and we need to move stuff from that DTN out to the wide area. How do we do that? Well, it goes through a bunch of stuff that it probably shouldn't be going through. It goes through our building or wiring closet switch or router, which probably has small buffers if it's not designed for the task at hand. It's going to be crossing our entire site or campus local area network, which has all kinds of other gook that's going on in there that we really don't want to understand. We have our global security policy that's applied on the perimeter firewall. We go through our site border router until we finally get to the outside world. So depending on the directionality here, there's so many things that are going to reduce our performance that even before we start doing this and getting it out of the gate, it's going to fail. And we don't want that, because if somebody just dropped a couple $1,000s on a brand new DTN and they plug it in, they're going to come back and they're going to yell at poor George. They're going to say, hey, I bought your DTN that you told me to at the SOX workshop and it's not working. Why isn't it working? Please tell me how to make it work. And there's just so much stuff that you have to consider in this architecture for this to be successful. So how can we be successful? I think that we need to go back and revisit what we're trying to do here. So this is the most simple and abstract cartoon that we can build with our Science DMZ. I'll sort of divide this into two parts. You could imagine a big dotted imaginary line that separates out the enterprise world from the DMZ world here. Let's see. I guess I don't really have a. Yeah. There we go. I do have a laser. All right. So maybe the laser will work here. Oh, nope. I guess it doesn't. All right. Anyway, if you can see my pointer, draw a big demarcation line that goes right here. So I'll deal with the DMZ part first. What we're trying to do here is we're trying to establish this clean, high bandwidth, wide area path. And what that means is that we want to minimize the number of hops that we have to deal with here. We want to minimize the security disruptions, but we want to be able to go from our high performance data transfer node out to the outside world as cleanly and as efficiently as we possibly can. So that's the first step that we're trying to optimize for. The second part is, how do we get stuff onto it? Well, in our toy DMZ design, maybe this isn't linked up to our institutional storage or anything like that. So if it's not linked up to our institutional storage, we need to hop information onto it. That information probably lives over here somewhere. We can hop it through this infrastructure if we need to, through this firewall. And because it's this low latency LAN path, that's not going to be much of an issue. Think back to that diagram that I showed of the graph, where even if we do have packet loss or something like that, that's on a very, very low latency path, I can hop it over there, deal with a little bit of packet loss, and it'll work out okay. What we are trying to optimize for is that long path situation, though. This to something else, to some supercomputing resource, to some international resource. And that's not going to have a lot of friction or anything like that that's going to prevent it from doing this. What does our security policy look like? Well, we're going to be applying it here, and we're going to have it be applied at a per service security policy basis, right? So we don't have a firewall to block against everything, but we know everything that's going on this box right here. We know that it's running a tool like Globus or GridFTP or Ruscio or any of the advanced sort of data movement tools. We know the ports it needs to have open to it. If we really want to lock it down, we can even say it can only talk to certain RNE routes or even certain IPs. And what that's going to mean is that I can apply all that in the silicon on the device right here and be just as assured that nothing bad is going to happen as if this thing were sitting in the path blocking everything, where I would put in the exact same set of rules, except I don't have to cross the data plane of that firewall to get there, right? So the data plane is able to work just as cleanly and just as efficiently. We're still blocking all the same stuff right here. So some people may be thinking, well, what if I need to have SSH open on this? Do you? Do you need to have SSH available? You can have it be out of band. You don't have to have it be listening to the big old wide outside world. Maybe you only have it listening to the IPs that may exist on your campus network here, right? There's many ways that you can crank the security up on this to make it as secure as possible. Yes, it is exposed, and yes, it is sort of available out here so that it can talk to the outside world, but it has that one task, and that one task is data movement. So I need to pause for a drink, but I will wait for people to ask questions if they have them.
Jason, so I'm curious, so it seems like you're implying like having a host firewall is okay on a DTN? If you need to, like if you need to limit it to an internal LAN IP?
If you need to run a host firewall, you certainly can. I would still argue what you're trying to get out of the host firewall. So what do you think the host firewall is going to get you versus trying to apply the security policy on the router? If you're talking, I can't hear you.
Well, no, so I'm thinking purely in terms of performance. So it sounds like you're saying that the better place to put that access control rule is on the router versus a host firewall.
Well, I was asking a different question first. Why do you think you need it?
Well, I'm just following up on your comment that if you want to limit access to it, you would put in some kind of rule that would limit it to an IP, a specific IP. So I'm wondering what your recommendation is there. Would it make more sense to put on the host DTN or on the border router?
So any firewall software or hardware is going to slow things down.
Right.
I guess maybe we're not meeting each other here in the middle. I'm trying to understand what functionality you think a firewall is going to get you versus an ACL. Maybe I'm missing your question.
Well, I'm asking more in the general sense. I don't have a specific case here. I'm just asking in the general sense. So okay, let me ask it a different way. What would you recommend for doing the limitation of that IP that needs to access the DTN?
It can be implemented as an ACL much more efficiently in the silicon of a device like a switch or a router than it ever could in software. Because with software, anytime that you have something that's going to try to track state in particular, that takes time. And any time it takes time, it's going to slow down the way that the protocol is going to behave, right? So really the rule of thumb is if you're going to pass it through something that's going to try to track state, you're going to take a hit. It may be a tiny hit if it's implemented at a host level versus something like a bump in the wire, but it's a hit nonetheless. With something like this, you don't need to process an ACL by going up a layer in CPU, right? That's something that can be applied at the network layer within the device itself. That's why something like a list inside of a device is always going to be faster than anything that's going to try to take deeper meaning about what that packet is trying to do.
That's exactly the answer I was looking for. Thanks.
Okay. Do we have any other questions?
There's an interesting one in chat about V4 versus V6. I don't have any good answers on that off the top of my head.
I can't see chat, George, so if you want to repeat it.
Yeah, absolutely. The chat is, Dan is asking, can you comment on IPv6 versus IPv4 and how it may affect speed or functionality?
You know, in the grand scheme of things, they both should work at about the same performance, but we do have lots of examples where the IPv6 stack sometimes works better and sometimes it works worse. Those are dated a couple of years ago, so we're getting to the point now where protocol is really not an issue. The only issue that we've seen with it is that if you're going somewhere, usually internationally, particularly to sort of the emerging regions like Asia Pacific and Africa, where they're able to get IPv6 allocations versus IPv4 allocations, sometimes it's going to go faster because there may not be, and this is going to sound bad, there may not be a lot of security in place over V6 because who uses that crazy protocol, right? So we have evidence of science projects in China and other places where V4 performance was clearly being impacted by some security scanning. V6 wasn't under the same scrutiny. So take that for what it's worth. Any other questions right now? Okay. All right, so where does the capability live? So there's two sort of schools of thoughts here. You know, when we looked at this, it's grafted onto the side of our existing network. Do we want to create an enclave like this for science use cases that are designed specifically to facilitate them? Or do we want there to be a drop-in replacement of our existing network so that we, you know, basically build out the Science DMZ to everybody's desktop? If you're thinking about going after CC star money, you know, you have to think about these two things. We usually like to encourage people towards number one. Number two, you can do it, but there's other things that you must be aware of if you're going to take this approach. So a couple of pros and cons here for the enclave idea. You do gain a deeper understanding of use cases and traffic flows and security if you're building something brand new off to the side and then you're moving your use cases onto it. You can build it to spec. You can ensure that you are getting buy-in from your various user communities. It's easier to operate long-term because it has fewer moving parts and fewer users. This will not be the Wild West unless you make it into the Wild West. It is arguably cheaper as well because it's fewer things. If I go back to that picture, you know, you can get your base Science DMZ going with 3 pieces here, right? Well, 4 if you count the interface that you need to have off your border router. In terms of cons, it is a little bit more time-consuming design because, hey, you need to go out there and you need to ask all the people what they're trying to do, and you have to pull in some people, perhaps like us, to help you with this. And it does require some dedicated staff to try to handle the operation and the onboarding because it is a dedicated science enclave, right? If you want people to be able to use it, they need to have accounts and things like that and understand what the limitations are on the data and all this other stuff. It's not going to really be the same as an enterprise network. If you're just going to go out and try to do the whole network upgrade, that's easier because, hey, you just upgrade entire chunks of things to support bigger speeds and feeds. And everybody is now capable of that higher performance, you know, and that also comes with the added benefit of there should be no excuse for people not understanding how to use this because, hey, it's available to everybody. But your cons here is that the security profile becomes incredibly harder to defend. You don't know what's going on. It is the Wild West, right? It's just a bigger version of your enterprise network, and now you've allowed people a little bit more ability to try to use it for high performance applications. It becomes more expensive as a result of this because instead of just upgrading one or two key components to support the high performance use cases, now we have to upgrade everything to support those. And you don't have an understanding of who is doing what. You know, it could be email, it could be cryo-EM work, you know, you really don't know. So we're going to pivot a little bit into what you need to buy. Requirements for Science DMZ gear are different than enterprise, and you don't need to go out and buy the biggest and fanciest things. The DMZ boxes really only need to do a few things, but they need to be able to do them very, very well. And there's also this temptation that we can probably go a little bit cheaper on these things because, hey, it's only doing a couple of these things, right? You don't always want to go that route, though, because if you skimp on some of these features that you absolutely need, it's not going to perform like you think it's going to work. So what are we optimizing for? This is sort of the most common use case that we deal with here. It's the multiple ingress of data flows and a common egress path. So in this situation, if you have your DTN traffic, which is often bursty by nature, coming in and hitting this switching fabric right here, but you also have this background of competing traffic and competing bursts, what's going to happen once we get into the inside of this thing right here? We need to make sure that it has enough buffer memory and enough smarts and intelligence in there to handle that traffic as it's coming in, because if it doesn't, this is where all your queue drops are going to occur, and this is what's going to impart packet loss into your TCP flow. Often this is at microsecond timescales, and it's really, really hard to measure, and it's really, really hard to understand, which is why you have to spend a little bit of time on the front end figuring out how to design it correctly. So what's important here? Deep interface queues or buffer is really the most important thing. The output queue or the VO queue, it really isn't what we're looking for in this case. What TCP sees is what matters most, and fan-in is not going to be your friend in this situation. We also need to have good counters. We want to be able to reliably count everything that goes in and count everything that goes out. And if we don't, then that's going to be a problem for when we're debugging and trying to do things a little bit later. And then the single most important thing here is that single flow performance should be wire speed, and you should be able to measure that with a tool like Perfsonart. So what's the inside of a switching plane look like? It looks a little bit like this, highly simplified. We have a bunch of input links, we have a bunch of output links, we have a routing function that's in the middle. Data is going to be arriving from multiple sources. The buffers have a finite amount of memory. Some of this may be per interface basis. Some of it may be just a big old shared pool that all of them are trying to eat out of the same time. No matter what the case is, it's limited. It's not unlimited. So if you throw a bunch of information on one of these links in here and the others are already chatting and starting to fill up as well, that's when you're going to start to experience the queue dropping behavior here. How do you get through this fabric? There's going to be a processing engine which is going to extract the packets, figure out where they need to go, and send them on their way. You're going to have delay as you go through this entire thing. That's, you know, that's a given. But we want to prevent the situation where we're having packet drops. So we need to have enough buffer memory that's available for all these different use cases here. How do you calculate that? Well, there's a rough calculation that you can do. It's called the bandwidth delay product. And this is the amount of quote unquote in-flight data for any TCP connection. And I'm doing this for a single stream. Change your math if you're doing multiple streams. But if I have an expectation of being able to go 10 gig across the country at about 100 milliseconds. Convert your bits to bytes and do all the math. Basically, you end up needing to have about 125 megabytes of buffer memory that must be available to support that one single flow. If you are a regional network or something larger, you of course have to have a lot more than that because you have big flows that are coming through you all the time. If you're a campus network, campus core, campus edge, you should have a lot as well. The problem that we run into is that if you connect up something, one of your DTNs, to a little top of rack switch that only has about 4 to 8 megabytes of buffer memory available for all of its interfaces, that's going to be a big problem. Buffering isn't important on the LAN. That's why the little tiny pizza boxes that live at the top of the racks are usually designed to be quote-unquote cut-through devices because they work in low latency environments, data center environments. They assume naturally that all the stuff that they need to talk to is going to be milliseconds away from each other, single-digit milliseconds away from each other. So even if we're going to talk 10 gig on 1 millisecond, we don't need a whole lot of memory. We only need, less than 2 megabytes there. If we're going to be talking on the WAN, that's where you need to have all that stuff available to you so that you can really ramp up your performance expectations. So what happens when you have buffer limitations on a TCP flow? Well, over time, it looks sort of like this. When we get to the point where we exceed a buffer, that's where you see these black lines start to show up, and that shows up as retransmissions. TCP, of course, is resilient. It'll sort of ramp its performance up as time goes on, as it experiences those losses, but then it also cuts itself down whenever it experiences some of those buffer loss behaviors. And Jorge's exercises on the 15th, you'll get to experience a little bit of this firsthand. But this is why you need to have enough memory available within your switch to try to support these different things. So I'm going to take a pause for another drink. If we have any questions, I can entertain them.
Good afternoon. Hi, I do have a question. You mentioned about 125 megabytes of buffer. I think you were saying 10 gigabits per second on a cross-continental link. Or was that your example, 100 milliseconds?
Yep, this is just to make the math easy. If you're going about 100 milliseconds, which, it's roughly across the country, and if you had any expectation of getting 10 gigabits per second, you would need to have that much memory available at each hop.
Well, so I figure I get how you would need that at the sending workstation, because you have to the sending workstation cares how many milliseconds it is to the other side and back. But on a hop, let's say right in the middle, that has a link that's X number of gigabits per second, doesn't it just need enough buffer to keep that one link saturated? And that link might only be 1 millisecond long.
So remember that TCP is a sliding window protocol. And in a sliding window protocol, you're sending out a certain amount of information end to end. And all that information has to get to the other end before we can acknowledge it and then send the next window that's going to be coming. If we look at the way that an iPerf or anything like that performs, basically it's going to start with a smaller window, and it's going to slowly but surely ramp its way up to larger congestion window sizes. And that directly translates into how fast your throughput is going to be. So if you ever watch iPerf over time, you can see that the congestion window is growing as it's able to do so. To get 10 gigabits per second, you need to be able to throw 125 megabytes in each sliding window. That's basically how the protocol works. If you ever take a hit, it's going to half that and half it again and half it again. But if you don't take hits and you're doing well, it's going to try to ramp it up until it gets to sort of its terminal velocity, so to speak. So what does that mean? That means you have 125 megabytes of buffer of data that is in flight, and that has to go over every single link along the way. Some links may be over provisioned. They may have a lot more available. Some may be under or busy and have stuff that's going on. But the point is, your individual flow needs to get that information to the other side. Otherwise, it will not succeed.
All right, so, and thank you. So I see if you kind of do some back of the envelope, that's 100 milliseconds of buffering at the sending host workstation. But to imply that you need 125 megabyte buffers at each hop from here to California, you're going to have 100 milliseconds of buffer at each hop. That does seem like a buffer bloat type of situation that could start to occur.
So we're not dealing with the same sort of speeds and feeds that we would with our cable modems, right? The 100 milliseconds that you may have buffered up in some core router on a research and education network, it's going to be quickly consumed by all the other traffic that's going on right there. You know, on ESnet, we don't measure our buffers in megabytes. We're measuring them in gigabytes and hundreds of gigabytes. And that's just necessary for being able to handle some of these large-scale flows, particularly from 10 and 40 and 100 gig connected hosts. So if you are your one little 1 gig host and you're the only one who's using that big old 400 gig provision network, you will see a tiny bit of additional latency, but that's not what we're optimizing for here. We're not optimizing for the video latency use case. We're optimizing for the data movement use case. So while it seems like it's a lot, it's necessary. Otherwise, it's not going to work.
Excellent, thank you.
Do we have any other questions? Okay. So I need to do a time check here. I think that I'm almost at the end of my time here, so I can skip through some of these because Doug is going to go over Perfsonart next, so I will skip that piece. Ken has already talked about data mobility. So let me go into security and policy, and then we'll sort of wrap it up here. The goal here is we want to disentangle the security policy and the enforcement for science from business. We don't want to touch the enterprise and business side. We want to stay as far away, if not even further than that, away from that, because that's all good. That's been designed, it's tested, and we don't want to touch that. Science traffic is different, though, from a security perspective, because it does have that narrow application set. You're not going to be doing a bunch of other stuff within this network beyond data transfer, data streaming, things that are related to that. You should not have printers, document readers, web browsers, HVAC, financial databases, and any of that stuff should not be within the Science DMZ confines. And the security controls that are implemented to protect the business resources are routinely the reason why we have performance problems. So we want that separation because we can allow each of those to be optimized. So this is a security architecture because it allows for that better segmentation of the risks and a more granular application of controls for those risks. What we're trying to do with this is we want to limit the profile for the high performance data transfer applications as much as we possibly can, and then apply controls for those data transfer hosts. We want to try to avoid including any unnecessary risks or unnecessary controls. So you, in effect, are removing these degrees of freedom, and you're focusing on what is necessary and only what is necessary. And I would argue that by thinking about it this way, it makes it easier to secure and to achieve that higher performance as well as troubleshoot, versus trying to figure out why something isn't working, because it doesn't have a whole lot of latitude about what it's supposed to be doing. It has that one job, and you can secure that one job as much as you possibly need to. So think about network segmentation here. You know, all those other networks that you may be responsible for in a day-to-day, the residence hall networks, business application networks, networks that are there in the research areas, there's all different sort of risk profiles in all of those. And it makes sense to try to segment along those lines. You're probably doing this already, so hopefully this isn't news to anybody. You know, if you're doing support for things like HIPAA or PCI DSS or anything like that, you know, those are in place and they have their own controls that are applied to them already. Think of the DMZ network in the same vein. You're going to have a set of controls that you apply to make it successful. Using the DMZ to segment research traffic, particularly traffic from specialized research instruments, can improve your entire campus security posture, as long as you're talking to the people who are using it, figuring out what the risks are, and then applying those cleanly. So before I move on, you know, we can talk a lot more about security. That's not what this talk was meant to be. So if people do have questions about this, it's probably better if we follow up with those offline. All right, so last couple of things here. We've given you a lot of information today. This requires collaboration within the organization. Everybody that is going to have some stake in this needs to be at the table as you go about trying to do the design, the policy, and the enforcement. What does that mean? That means security people need to be on board, the infrastructure people need to be on board, and leadership needs to be on board. We're talking some crazy stuff here because, hey, we're about to build a network that's not going to have a big old firewall in front of it, right? If something gets compromised, people get fired for that, right? Nobody wants to end up on the front page of any of the news websites saying, oh, look, here's another security breach. It's a part of doing due diligence to understand what risks are and how to mitigate them. And all the things that we've said here today, you can identify the risks cleanly and you can certainly put mitigations in place. It's just about making sure that all of those align with what the overall goals of this enclave are supposed to be and how they fit into your organizational profile of these sorts of things. This is meant to be a strategic asset because it is meant to accelerate a lot of the research use cases. So because it is strategic and because it is something that benefits everybody, make sure everybody is on board as you try to implement these things. So what is a sensible usage policy? What I mean by that is that we need to have something that is usable by the scientific community, and we need to define what they really want to do with this. Do you let them come in and plug in their old Windows laptops directly to the border router? No, that's not what this is about. We need to talk about their use cases, understand what they are, and if they have data mobility requirements, it comes down to a couple of key categories. Either they need research data and they're either going to create it or they're going to be retrieving it from somewhere else. Once they have it, they're going to do something with it, probably analyze it, use computation to look at it, visualization. Maybe that's local, maybe it's not. You have to ask those questions. And then what happens after you're done with your analysis step? You're going to do something with it. Maybe it gets deleted, probably not. They're going to hold on to it. All of those things are a necessary part of that conversation for understanding what the use case looks like. So we would certainly recommend defining access methods. How do you share this information? If it needs to leave and go somewhere else, it probably is going to go through a DTN. That storage is going to plug in, or that DTN is going to plug into storage. Maybe it plugs into institutional storage, maybe it's somebody's personal disk, whatever the case may be, you need to make sure you understand what they're thinking they want to do. There's going to be certain tools involved. There's going to be people who need accounts. Consider trying to define what that access method looks like before this thing is put in place, because once it's built and people know it's there, they're not going to wait around for you to try to figure out what your policy is going to be. So define the policy first. Just define an AUP that goes along with said access methods. Who can, should, and will be sent information. What happens when something bad happens? How often are you reviewing this? Are the researchers allowed to come in and help you review it to make it either better or more secure or to fit their use cases a little bit better? We have some resources on the web that you can take a look at if you need more guidance on that. And then lastly, but probably just as important, define what your monitoring and measurement and security expectations are going to be here. You as the IT people get to define that. So you're the ones who are in charge of how you're going to monitor and how you're going to keep things up to date, and let the users use it. Be transparent. Say that there's going to be some monitoring and security in place to make sure that you're adhering to what the AUP and the access methods are going to be. But certainly let this be a conversation that is ongoing, not necessarily something that stops after you decide to put this in place. So, summary. Know the users, know the use cases. I can repeat that 4 more times, but I think everybody's heard enough of that at this point. It is a data architecture. You're trying to support ingress and egress of information at all the different layers. A lot of different moving parts that go into that, whether it be the network gear, the transfer software, the hardware, measurement monitoring, security. Don't get bogged down as much in that. Remember that it is about the data architecture and understanding what people are trying to do. Facilitate usage, because if you build it, they're not going to come right away. They need to understand how to integrate it and how to use it. And then have a good story for the long term, which is basically making sure that you can continue to have people adopting this, onboard them the proper way to do things, expand it, maintain it, because it will become a critical part of the infrastructure over time. So that's my email address. I'll leave that up. There's also the general EPOC help desk, which if you have a real problem, send it there or to me. We'll figure out where it needs to go. But I will stop now in case there are any other questions.
Jason, there was a call out in chat about feedback on an ASIC-based security device like a Corsa NSE 7000. Any feedback for security appliances, firewalls? I think in the past they've been called network inhibitors.
Yeah, I don't know what a Corsa E6 7000 is. It sounds like a killer robot. My standard answer for stuff like this is get a demo unit, put it in the network, put a hardware-based tester or a Perfsonart tester on one end and measure how well it does. It's hard for me to be able to know what's going on in something like that unless I get a look at the architecture. But like I said a little bit earlier, anytime that you have something that is either going to maintain state or otherwise delay the flow of a packet that's trying to traverse the network, that's going to impart delay into the TCP protocol, that's going to cause pile-up and or selective acknowledgements or retransmissions, and that slows things down. The only way that you can usually figure it out is if you can demo it and try to profile how it's working.
Jason, I apologize if I missed this, but at one time there was a list of small buffer versus big buffer routers and switches. Is anybody maintaining that?
Yeah, so Jim Warner of UCSC, who has retired, he's still with us, of course. He's kind of active in the community. His webpage is still up there. It's linked off of faster data. I bet one of my colleagues that's still listening can probably plunk the address into the chat window. I want to say it's one of the UCSC web pages. It's still there, but because he's retired and not updating it as much, it's probably dated to his retirement date of about 2019. But there's a good indication there of some of the major devices from the major manufacturers.
Great, thank you very much. Somebody did drop it in the chat. Thank you.
Any other questions?
I don't think so. Thank you very much, Jason. Appreciate it. A lot of good feedback in the chat on that.
All right, well, thank you all. And now I need to figure out how to stop sharing. Yep, there we go.
Are you ready for us to roll into your Perfsonart talk?
Yeah, we can go ahead and jump straight into that.
Great, thank you.
Okay, make sure I got it up here. And then teach myself how to use Teams really quickly. Okay, hopefully that is my Perfsonart presentation.
Yep, it looks good. Thank you.
Okay. So we're going to be covering Perfsonart, obviously, but this is going to, in some ways, tie together several of the talks we had this afternoon, including even back to a little bit of understanding your researchers and maybe some of their frustration with the network or getting them to adopt certain policies and certain ways you want them to think about using the network. So there'll be a lot of, I don't want to say duplication, but we're going to cover some of the same ground, but look at it from a little bit different angle. So we've talked a little bit about this already, but a lot of what we deal with when we're talking about research and education networks is that they are very complex beasts that we don't have control over all of the parts. In fact, you very likely on your network only have control over maybe not even the entire network. If you're a large institution, you might only control the research network or a small portion of your commercial production network. But we still have to get data from end to end. We have to move data either across the state, a continent, or maybe over an ocean. And so you have this mishmash of different networks operated by different network operators that may or may not have different ideas about how networks should operate. And all of this together means that data transfers aren't really as simple as, or at least high-speed, high-performance data transfers aren't as simple as just clicking a button and the data gets there at whatever wire speed you can support. So there's kind of this magic spaghetti that makes the whole thing work, and we call it the Research and Education Network. And you even run into situations where maybe the data is not taking the same path. It's going out on one particular path and coming back on another particular path. There's a lot of complexity that gets mixed into this that causes data to not, or basically data transfers to not perform as well as we might like. So in order for a transfer to work at a high performance, high rate of speed, all the pieces have to work together seamlessly as though you were operating the entire network and you had access to all those pieces and parts and could actually streamline and maintain those. We have to have data mobility. We talked a little bit earlier about HPC resources. We've talked about DTNs and data availability. We've even talked about instrumentation and treating the network as part of the instrument, because you might not have a giant particle accelerator on your campus like CERN. In fact, no one does, because there's only one CERN. So to have access to large instruments and radio telescopes that are not one instrument, but maybe a collection of instruments distributed across the globe, we have to have seamless end-to-end integration to make that all work. So our goal is to support scientific use and to understand how the users are using networks and what they're interested in using them in. So this slide here is really meant to show that as the collaboration scale increases, as we're talking about larger and more complex projects, we have fewer players, but much more intensive data requirements. The example on the far right, LHC, you're talking about a very, very large scale collaboration that involves scientists on every continent from many, many countries and huge, huge petabyte data sets. But there's only a few collaborations out there like that. On the smaller side of things, we do have a lot of smaller type of projects that, while they may not have petabytes and petabytes of data, we might be talking gigabytes or tens of gigabytes, there are far, far more of them, and they still have to transfer that data. The fact that they have smaller amounts, but there's more of them, doesn't really change the equation. Data mobility is what we're after, and supporting those scientific use cases. Understanding the scope of it can help us kind of tune and test and optimize things for those specific cases, though. So kind of tying back to earlier, Ken kicked off a talk about data mobility. And so we were shooting for that 1 terabyte in an hour as kind of a benchmark that we're looking at for a high-speed modern R&E network. So we talked about needing about 2,500 megabits or 2.5 gigabits per second. You can see that in this table. This table doesn't account for, some of the overheads and realities of TCP, but it gives you a rough idea. The real take home from this slide, honestly, is that connectivity, if you're in this green area, it means you have 100 megabits or less of wire speed available to you. So you can still transfer fairly large files at relatively high speeds. We're talking a 10 gig file you can transfer in 1 hour or so, even at those types of speeds. The take home really is that these only apply if everything is working perfectly. If all the pieces come into play and you're actually getting the full performance out of your network. The problem is finding those performance issues can be complicated, and users don't have access to the network. As a network administrator, you might have access to the guts and pieces and parts of part of the network, or possibly your entire network, but the end user really only has access to the computer at the end of it. The other thing too is a lot of times it's hard to communicate actual needs from researchers to network people, and from network people on up the stack to maybe the CIO's office. And understanding those use cases and what researchers are actually trying to do versus how the network was constructed or the paths that they're using to transfer that data, that stuff is all out of the researcher or the end user's control. They may not even know you have a Science DMZ. They may have no idea what a Science DMZ is. They may not know that they should be hooked up to that, or that that's available to them to do high-speed transfers. And because of that, they may have had experiences in the past that, oh, well, I tried it once and it didn't work, or the transfer speeds were terrible, or maybe they had a run-in with a former IT staff member who really didn't help them out, didn't give them the support they were looking for, and so they got frustrated and said, you know what, it's easier for me to put all this data on a disk and I'll ship it. And then that kind of thing over time becomes a habit. Now we're shipping disks all the time because that's the way we've always done it. It works, you know, it's reliable, and I just don't want to mess with this again. Scientists want to do science. They don't want to do IT support. They don't want to figure out why the network isn't working the way they think it should be working. They just want to do their science. And so that's where we come into the capability gap, which is where the end users don't understand the network because it's too complicated and they don't have enough visibility, or they just don't care to because they have other things to do with their time. And then the other side of that, on the network side, where you have people who understand the network and what it is capable of, and possibly how to tweak things and make things better. And these are the kinds of problems that we run into when we're trying to talk about high-speed data transfers and understanding what reasonable performance is. And we'll get into a little bit of that as we move through the presentation here. I'm going to skim through this section because Jason did a really, really good job of talking about network performance and TCP behaviors. And there's a couple slides in here that are going to be duplicates. And we don't need to rehash all of that. But the reality is that TCP is a very old, creaky protocol. It's been around for a long time. It was designed around being robust in terms of your data will get there. It might be slow, it might not be pretty, but it will absolutely get there. In fact, the TCP protocol was actually written specifically to hide errors and problems from the end user. So it's designed to get data to where it's going without letting the end user know why it's slow or why things aren't working the way maybe the user thinks it should be working. And it was built around networks that were inherently slow and lossy. And we're in a different era now. We're in an era where networks are fast and packet loss is usually relatively small in the grand scheme of things, but we're using a protocol that wasn't designed around the kind of hardware and software that's available today. But we still run into a few things, you know, in terms of buffer sizes and a few other things like that that are still prevalent as well, and those can really have a drastic impact on how TCP performs. So really at the base, we need to know who our users are. We need to know how our network performs, or how we think it should perform. But then we actually need real data that shows how our network is actually performing and not just how we designed it to. Is it actually doing what we thought? And then once we know that data, does that performance meet the user's expectation? Or does the user even have a concept of what that expectation is? Do they even know how fast things should be moving? Where can the problems be? Literally anywhere along the path. So you could have links that are congested between two hops that you have absolutely no control over that are 2/3 of the way through the transfer. You can have intra-campus links that are congested because there's not enough bandwidth between the researcher's laboratory and where you know, the data actually exits the campus, or where the DTNs are, or something along those lines. And there could be latency problems that are masked within a campus because, or packet loss problems that are masked within a campus because at low latencies, TCP behaves the way we think it should. So if you've got less than 10 milliseconds of latency, you can actually have really significant packet loss and still be getting 1 gig performance or 10 gig performance or 40 gig performance, because TCP can really cope well with errors when you have very low latency. The problem comes when you get outside of that 10 millisecond barrier and things really, really start to fall off. And again, now you're dealing with things that are absolutely outside of your control, and you don't really have any visibility. You may have network testing on your campus. You might know how it performs from the core to the edge, or you might know how it performs from the edge to your internet service provider. But what about the transfer you're trying to do across the country, or your researchers trying to do across the ocean? You probably don't have any real visibility into how the entire end-to-end link is working. Jason did a really good job of explaining this slide, so we're not going to go into it again. What we're interested in looking at, though, is the concept of soft network failures. Now, pure hard failures are easy to find. They're when there's no connectivity. You can't send email, the researcher can't contact the person on the other end of the stick that they're trying to do a data transfer with. Those things are pretty easy to find because somebody usually calls you up and says, I have zero connectivity, I can't see the internet, nothing works. Then you just start looking around for where is that problem? Did a switch die? Did a cable get unplugged? Something along those lines. Soft network failures are a little harder to find, and they're really what we deal with more often than not, which is where the networks, there's connectivity there, but we're not getting the kind of performance out of the network that we're expecting to be there. Again, TCP is designed to hide these kind of failures from the end user. That's actually part of the whole design of TCP. And these kind of failures can sit around for a really long time because the network is quote unquote working. There's connectivity, I can ping the other end, I can do a transfer, it might not be good, but I can get there. So soft failures are the kind of things that really inhibit science data transfers and the kind of things that can really cause users to maybe lose faith in the network or maybe prevent them from even being able to do the kind of research they need to do. So how much should we really care about soft failures? The answer is honestly a lot. Soft failures are probably one of the largest problems that exist in any network today. And honestly, my day job completely revolves around finding these soft failures. And what could those look like? Could be a copper network cable that somebody has running underneath a chair mat. And so every time they roll back and forth, it absolutely, mashes that cable. And over time, there's still connectivity there, but we have packet loss issues. It could be dirty fiber. It could be an underbuffered switch. It could be an overloaded CPU at the other end that just can't keep up with the amount of packets coming in. There's a lot of things that could be the cause of a soft failure. It's not just necessarily a network capacity issue. We don't have enough network capacity to move this data. So underbuffered switches, we've talked about this several times, but this graph kind of brings home what we've been talking about in terms of not having enough buffer to cope with high-speed data transfers. So these are all simulated with 2 gigs of background UDP traffic. And so we can see that some of these switches at the top can absolutely cope with a sustained 7 to 8 gigs, almost 8 gigs of traffic with 2 gigs of background traffic over 50 milliseconds because they have enough buffer to cope with that. But once you start getting into switchgear that maybe is not designed for long distance transfers, maybe it's a less expensive switch that you would have in the top of a rack in a data center where you don't need buffer because you're only going 1 to 2 milliseconds away, they start to fall apart doing the same kinds of transfers over 50 to 100 milliseconds. So we posted it in the chat, but there is a list there of switches and buffers and why that stuff matters. Why do people shy away from switches that have deep buffers? Well, buffers cost money. And so when you're looking at a switch and it's a 10 gig switch and you can get this one for cheaper than that one, sometimes that drives decisions. And so it's very, very important to understand the specific kind of hardware you're buying and how that's going to affect performance if you're talking about transfers that aren't just local in nature. Again, Jason talked about the Science DMZ. The point I want to highlight here is Perfsonart is in the slide because it's an integral part of your Science DMZ. Because what we need to be able to do is to simulate actual transfers and understand actual network performance. We're going to talk a little bit about how Perfsonart allows you to do that. But when we talk about hardware considerations and what switches are appropriate and what kind of router is appropriate and what kind of DTN we're building, when we're looking at that whole picture of the Science DMZ, there needs to be consideration for Perfsonart nodes and where testing is going to occur and kind of what our testing goals are in terms of where we're placing these in the network. Do we just want to know what performance looks like over here at the WAN and that's all we're interested in? Do we want to have one deeper into the network so that we can simulate a transfer basically all the way from the endpoint where the researcher is starting that transfer all the way to whatever endpoint that they're trying to reach? Those kind of design considerations, when we're building a Science DMZ, can drive the kind of hardware we buy and how much of it we buy and where we place it. So now we're kind of coming to the crux of what we want to talk about. Well, what is Perfsonart? So we've talked already a little bit about the idea that you can't control every single piece of your network. You can control the gear that you buy on your network. You can control the types of data transfer protocols you use. If you've got researchers that still want to use FTP, there's ways to get around that. You could talk them into something else, or you could just block FTP. But SCP and rsync are still available. They're slow. There's a lot better options out there. We usually drive people now towards Globus because they just have a lot of amazing data transfer tools and make that all very simple. You can control those kinds of things. You can control the configuration of your local gear, hosts, servers, network devices, all those kinds of things, how you use diagnostic tools and what kind of diagnostic tools you use. Those are all under your control. Now, you can't necessarily control the configuration of remote gear on the end, or maybe gear in the middle of that transfer. You can't control failures on the other end, or what kind of response time they're going to get. Maybe your network, you have a maximum of a 2-hour response time, and maybe the network they're connecting to on the other end is a 2-day response time to a problem. Getting someone to care can be a really interesting thing when you're dealing with long distance transfers, and the person on the other end has bigger fish to fry than maybe that research. Maybe they're dealing with something else, and you're trying to get them to be interested in your project when they have other fires to put out. So all networks do some form of monitoring, right? We've got, whether it's a very, very basic speed test, or maybe you're using a really complex monitoring suite. You've got some sort of network monitoring going on in your network, and you know how things are operating to a certain extent. But wouldn't it be nice if we had more than just point-in-time data? Because realistically, when we're looking at network monitoring inside of a network, it's usually very, very point-in-time data of specific hardware and how it's operating right now. And even if you have data over a period of time, again, that data only reflects what's going on inside your network. But being able to see performance over time to partners that are scattered all over your state or country or all over the globe, and having basically references and reference data that can look back over the span of weeks or months or years, and being able to see how that performance varies over time, and whether we're actually maintaining a minimum standard that we were happy with, or whether something's happened in the meantime. Those kinds of things are data that would be really, really useful when you're trying to keep track of your network and all the pieces in between, and your network and the network on the other end that you're transferring to. And that's where Perfsonart comes in. So Perfsonart, really at its core, allows you to fix and see the problems that you can't normally see without it. So when we're talking about a Science DMZ or a high performance network, pardon me, I'm going to grab a drink here. When we're talking Science DMZ or a network, we need everything, as we said earlier, to operate basically flawlessly. We need consistent behavior. And if we're going to get consistent behavior out of that network, it means all the little individual pieces have to be correct. Perfsonart gives us the tools to see those individual pieces and get a picture of performance as a whole. It gives us a way to view the network in the way we couldn't before, because now we can start to look at the middle of the network, the far end of the network. We have visibility that we absolutely did not have Where before maybe the only thing we could prove out was our network. Our network works fine, and that's the only piece we need, or that's the only piece we could show, I should say. So Perfsonart really at its core is just a collection of readily available, pardon me, readily available open source network monitoring tools that a lot of you maybe are already familiar with, like iPerf, Traceroute, stuff like that. But what Perfsonart brings to the mix is it's packaged all up into one open source platform. And the real magic that makes it all work is the P-scheduler piece in the middle that allows you to actually schedule and run tests against a variety of hosts that aren't your own. You can work with Perfsonart nodes that are on other networks at other endpoints, and you can schedule tests with them. If you're just running iPerf, you can't really run iPerf against somebody on the other end unless you call them up and coordinate it, and they start iPerf up and they're listening for the test, and you have those kind of things coordinated. Perfsonart takes all that out of the mix. If you've got a Perfsonart node or multiple Perfsonart nodes set up at your institution and you're transferring data to TAC, or maybe you're transferring data across the ocean to CERN, or maybe you're transferring it to APAN, if you have nodes set up along those paths, you can now start scheduling tests and understanding what network performance actually looks like without having to coordinate tests with other end users. There's just an expectation there that we have some visibility into research and education networks. So why do we need Perfsonart when things are getting a little bit better than they have? I mean, TCP is less fragile than it was. We talk about in this slide that Cubic is now the default, but we're starting to look at other things now. We've got BBR, we've got other things out there that are a little more congestion, agnostic, and they don't get as upset when there is congestion on the network. Larger buffers are becoming standard in switchgear. Again, we'll mention Globus is a really, really robust, reliable transfer medium. There's options out there that have made performance a little more accessible on a consistent basis. The problem is that wizard gap. Network users still don't know what to expect. They just assume that if you tell them you have a 100 gig line coming into your campus, they're going to get 100 gigs worth of speed to their desktop. They don't understand all the pieces and parts that go into making that work. Jumbo frame use is still pretty small. And across shorter distances, jumbo frames aren't as important as they used to be because we have more CPU speed, we have more RAM now. But when you're talking long haul transfers, jumbo frames still come into play. And in order for jumbo frames to work, you need them to work end to end. If somebody in the middle doesn't support jumbo frames, then you don't have an end-to-end path that you can use that on. Underbuffered switches still exist, misconfigured or underpowered firewalls, as Jason was talking about with Science DMZ. Those, anytime you have something like that in the path, you absolutely have the potential to kill performance. And those pesky soft failures we talked about earlier, those are the types of things that, because they don't present as an outright failure or loss of connectivity, those can go undetected and be sitting in a network for months or possibly even years. So we want to be able to simulate performance end to end. We want to be able to tell a user, if you do a transfer, this is the kind of performance you can expect. And we want to be able to do this to prove out our own networks as well. So in order to do that, we need to be able to transfer something across the long path. Because remember, TCP is not something we can simulate by pieces of a whole. You can't simulate transfer performance by saying, I know what my performance is from the core of my network to the edge, and then I know what it is from the edge to this first hop, and then I can get somebody else to do from the next hop to the next hop, and then finally from the next hop to the endpoint. Gluing all those pieces together will not actually tell you what an end-to-end transfer looks like. So the Perfsonart toolkit, as I said earlier, is an open source conglomeration of various open source tools packaged together, maintained. The default Perfsonart installation is based on CentOS 7. There are packages for Debian 9 or Ubuntu 16, but the Cent package that comes basically is a downloadable OS on a stick. You can download the image, install it, all the tools are there, everything has already been optimized to run with Perfsonart. The real magic, again, that's under the hood that makes this all work is that p-scheduler piece that allows you to run tests against the different hosts at any point you need to. It's super easy to install and configure. Usually takes less than 30 minutes. In my experience, it takes less than 15, and that's even on pretty modest hardware. I don't think I have a slide in here, but to run a basic node, you don't need a whole lot. 120 gigabytes of disk space is more than enough, 4 gigs of RAM, and any modern processor, if you're doing a 1 gig test, any modern processor will probably keep up with that. If you're trying to do 10 gig, then you're probably going to want something that's 3 gigahertz or better in terms of processor speed. But a bunch of cores don't really buy you anything because TCP, it's all single stream, so you just need individual fast core speed. So you don't need really intense hardware to stand up a Perfsonart node. When you start talking about 40 gig or 100 gig, if you wanted to have a Perfsonart node that big, we could probably talk to you about sizing, but honestly, the doing tests at those kind of speeds usually isn't particularly fruitful. So kind of a quick idea of how this gets deployed. Again, we talked about having Perfsonart in your network at multiple points. Now, Perfsonart does need to live out in the wild, woolly internet. You can put ACLs in front of it. If you've got it plugged into a switch at the edge of your network, absolutely stand up an ACL that says that I only want to accept tests from these research networks. For instance, ESnet has Perfsonart nodes that are scattered all over the place, but they have a blanket ACL that basically just says, look, we are not going to accept tests from non-R&E networks. So you could limit it to that, or you could limit it to just the partners that you're interested in testing with. But it does have to have a real-world IP address. It does not function well behind NAT. There are ways to make it work. It's not a recommended installation. Needs to be out there, have a real world routable IP address. And then from there, the idea of that is that you can have a node that is accessible and available for other people to test too. So while this is your node and you're using this for performance modeling, part of the aspect that makes Perfsonart work is the community aspect of nodes that are placed in various places around the globe, various points on research networks, where you can actually access them at any time and model performance. So you're getting something you can use for performance testing, but you're also part of the larger community that allows that node to be used. So again, we're kind of looking for a needle in a haystack. I don't want to beat this drum too much, but we're looking for those soft failures. The more Perfsonart distributions we have out there in the wild, that means we have more network visibility. For every node that gets stood up on a network, we now have another test point that takes another network path to get there, that we have deeper and deeper visibility into R&E networks, how they're actually behaving, what kind of performance we can actually get out of them. So this website here is actually a directory of Perfsonart nodes that are out in the wild, that are open, that are available for testing. And you can see we've got them spread all over the globe. There's definitely heavy concentrations in some parts. But you can go, if you have a Perfsonart node, and if you want to test to any of these available ones, you can go in and search for a specific country or a specific institution and find the closest node. You can even search by IP address. If you know just the first couple octets of an IP address, you can put it in there and see if anybody in that specific network has a Perfsonart node stood up that you can test to. The caveat with this right now is this is all hosted on a commercial cloud type of setup. So if you have a Perfsonart node that has no access to commercial internet, if it is locked down to solely R&E networks, it will work, but it will not be listed in this directory. It has to have some way to talk to commercial internet to let people know that it's listed in this directory and that it's available for testing. So there's a little point of confusion there, and I always like to point that out. We're working on a different solution for that, but right now that's just the way the services directory functions. So this is the mad dash. This is actually going away. I'm not going to say like in the next month, because that's not true at all, but in the next year, you're going to start seeing a move away from mad dash because we're going to be looking at some other alternatives that are Grafana based, and we've got some other things up our sleeve. But the basic gist of the mad dash is this is coordinated testing. So you can do your ad hoc testing whenever you want to. You can fire up a Perfsonart node and shoot off a test to a partner and understand what the performance looks like in that point in time. If you want to do the kind of testing we talked about earlier, where you want to do testing that shows what performance looks like over a period of time, whether that's months or weeks or years, whatever kind of data you can collect and for however long you want to participate, you would involve yourself or your node specifically in a mad dash mesh. And so this is regular coordinated testing between your node and a group of nodes so that you can understand what performance looks like over time, and you can have a better idea of whether a soft failure has crept in, or there's been a major network change, or maybe a routing change that you weren't aware of, because now you can understand what your performance should look like on a normal basis. If you're testing bandwidth 4 times a day, and it's always been consistent at 5.3 gigabits per second to this particular partner, and then all of a sudden you notice it's down in the 4s, and then a month later it's down in the 3s, you can go back in time and look at a graph of that data and say, yeah, there's been a steady decline in performance between our researcher here on campus and this partner that they're doing research with. Why is that? Can trigger those kind of investigations that lead us to find the soft failures that inhibit research and education transfers over time. So this is your visibility into the end-to-end performance that you don't have when you're just talking about on-campus monitoring. So the benefit of Perfsonart, we've talked about it a couple of different times, but it's that visibility, end-to-end transfers. What do my actual transfers look like if I was going to simulate performance between me and the outside world? But it's not just that. You are becoming part of a larger group of Perfsonart users out there that are also trying to model performance and want to understand what's going on with research and education networks. And it doesn't have to be just bandwidth testing. We do regular latency testing to understand what latency looks like in the background between nodes, and even just being able to run a trace route between 2 nodes. And the fact that one thing that oftentimes gets missed when you're talking about Perfsonart nodes and the availability of them out there is that you can use your node to run a test between 2 other nodes. If you want to see what a trace route looks like between something at, say, Berkeley, and then you've got a node that over in somewhere in Japan, like at NII, you could actually use your node, let's say you're in Philadelphia, to initiate a trace route between that node on the West Coast and that other node over in Japan and see what that pathing looks like. So the visibility, the ability to be a part of that community and understand what performance looks like and have those kind of baseline tests and also ad hoc one-off tests is a real benefit. The more nodes out there, the more visibility we all have to be able to understand performance. There's a couple other things, ways that you can be involved. We've got an announcement list and a user list. The announcement list is exactly what you'd think. As we release new versions, we can make that available and let you know what that looks like and what the changes are, that sort of thing. The user list actually gives you access to Perfsonart developers. If you have an issue, you can throw a question out there. It's going to be seen by a lot of really technically adept Perfsonart users, but you're also going to have the attention of Perfsonart developers. If you find something that looks like a weird problem with Perfsonart, you think it's a bug, you think it's an issue, or maybe you don't understand the setup or the way this test is running, chances are a Perfsonart developer is actually going to see that. So if you're thinking about standing up a node and you have any questions, even if you don't have a node and don't plan on putting one up for the next 6 months, jump on that Perfsonart user list And there's a lot of great information there. I think that answers a lot of questions. You're gonna see answers to questions that probably won't come up in normal documentation, and kind of get a sense of Perfsonart and how it's used out there in the wild and what kind of issues can occur. And so this last slide is just a rundown of a bunch of Perfsonart resources. Since we're making these slide decks available to everyone, I wanted to throw this in there. If you have questions, most of them will probably be answered here. But if it goes beyond something that's not in documentation, then that Perfsonart user list is kind of your next stop. Okay, that was a ton of information. I'll stop sharing here and I'll take any questions if there are any.
Is there a preferred hardware list for Perfsonart as well?
There is. There's actually, if you go to perfsonart.net, there's not preferred hardware in terms of you should buy this exact, PC from Dell or something like that. But we do have examples of these nodes have been used successfully. This configuration has been used successfully for 1 gig testing. And if you want to go to 10 gig testing, then these are the considerations you need to make in terms of upgrading that to be a little bit heavier duty server that can cope with that. And we do have some actual model number suggestions. If you're really, really just stumped and you don't know what you should be looking for, there actually are a few, hey, take these model numbers, go ahead and build yourself one of these. We do know that this works for this level of testing.
Great, thank you.
Yeah, hello. Can you hear me?
Yes.
Yes.
Yeah, thanks. Can you expand real quickly on, you made a statement that sometimes it doesn't even really make that much sense to do tests at 100 gig or 40 gig?
Yeah, if we're talking about, if you want to go for pure network saturation, saturation to do initial proving, then those kind of tests can make sense in limited applications. But in general, when we're talking about looking at network performance, we found that usually testing at, say, a 10 gig level, if you're on a 40 gig network, is more than enough to spot large scale issues. Because quite frankly, 100 gig to 100 gig transfers are really, really rare. Most people out there don't have a DTN capable of coping with 100 gigs worth of downloaded data at one given time. We're trying to model realistic transfers that we would actually see out there in the wild. And typically right now, 10 gig is kind of the baseline unless you're talking very, very large, complex institutions. And again, if you've got a significant problem along the path, even testing a 10 gig in a 40 gig network will absolutely highlight problems along that path, because you're not even going to get 10 gigs. Usually you're going to see, retransmits and performance problems that'll be readily available at lower speeds.
Great. Okay, thank you.
Any other questions for Doug? Okay, well, listen, I would like to thank in particular our presenters. Very grateful, a lot of great content here that Melanie has posted a link to the slide decks in the chat, and we'll be working to get the recordings posted right after, as soon as we can. I'd also like to thank the folks that participated here today. It was great to have such good questions come up, and to have good broad participation from across the country at least. I hope that folks will make time to come back for the hands-on workshop next week. I think it's the next logical step after going through something like this. We had as many as 122 connected today, so that's been fantastic. And if you have any questions or need follow-up, feel free to reach out to us here at SOX. or any of the presenters directly. With that, we'll end the session. Thank you very much. Have a great day.